Again, Chapter 1 is still more review, and we're going to go through a few problems of dimensional analysis for examples. All right, I'm going to do a few of these problems with you. They will get more complicated as we go along, and we'll do some in class also. So let's make a plan. We're starting with feet, and we need to get to centimeters. And I think the easiest way for me to do that, and there's more than one way to do it, is to go from feet to inches to centimeters. All right, starting off with what's given, 6.8 feet. Feet are up here, so I want to bring them down here, and according to the plan, convert that to inches. I know that there's 1 foot contains 12 inches. Make sure you cross off your units. Bring your inches down and convert that to centimeters. You do need to know that 1 inch contains 2.54 centimeters. That is one of those ones you need to know. All right, then we're going to multiply all three of these numbers across, divide it by 1, so that's sort of silly, and we end up with 207.264, that's a decimal point, centimeters, and those inches did cancel. Look at your sig figs. This says we need 2 sig figs, so your final answer should be 210 centimeters. Taking a look at this one, we have an iron sample with a mass of 4.5 pounds, and we need that in grams. So I'm going to go from pounds to, all right, kilograms, and then I can go to grams. Again, there is more than one way to do it, but since that's the information given, that's how I'm going to start. So 4.5 pounds, bringing pounds down. According to the plan, I'm going to convert that to kilograms, and 1 kilogram has 2.2046 pounds. Those will cancel. Bringing kilograms down, grams to here. 1 kilogram has 10 to the third grams. We're going to multiply everything in the numerator divided by the denominator. So we end up with 2041, let's see, kilograms canceled, left with grams. And according to this, we have 3 sig figs, so I need 3 sig figs in my answer. 2 ways you could have written this. You could write 2040 grams or 2.04 times 10 to the third grams. Either answer is fine. This was one of the more difficult problems we did last year. So let's take a look at this. 385 miles. I'm pretty sure we're going to need a long line for that one, per hour. So let's take each one separately. We need to get miles to meters. If we get miles to kilometers, then we can get that one to meters. So let's ignore the hours for now. Bring the miles down to kilometers. And 1 mile has 1.609. You don't need to know that one. I just happen to know that. That makes miles cancel. Bring the kilometers down and then meters. Remember, we're going to use King Henry died by drinking chocolate milk, and that is where the meters are. So we're going to, from kilo to meter, that's 3 steps. That whole system's based on 10. The bigger unit gets the 1, 10 to the third. Kilometers cancel. We're left with meters where we want it. Now I just need to get hours to seconds. So I'm going to bring hours up here to seconds. And I know that there's 3,600 seconds in 1 hour. Let's give that a try. So in this case, I end up with 172 meters per second. There's 3 sig figs, 3 sig figs. We're good to go. This is one you really want to pay close attention to. Wink, nudge, wink. Yeah, you really need to know how to do this one. Okay, so we're going to start off with the pounds. and we want the volume in cubic centimeters. So our final answer in cubic miles, sorry, our final answer is going to be miles cubed. Well, I know that with this grams, I can get pounds to grams. So let's start with that. 6.00 times 10 to the 19th pounds. I'm going to have to write smaller than that if I want to make it all the way over there. So 1 pound has 454 grams. I knew that. You would be given that, or you could look it up. I wouldn't expect you to memorize that one. Okay, now I have grams. To get rid of grams, I'm going to use this conversion right here. 0.92 grams to 1 milliliter. So that makes the grams cancel. Now I need to figure out how to get milliliters to miles cubed. Well, I know 1 milliliter is equal to 1 centimeter cubed. From there I could go from inches cubed and then to feet cubed over to miles cubed. Oh boy, so milliliters. So 1 milliliter has 1 centimeter cubed. And that made that cancel. That one's easy enough. Centimeters cubed needs to come down here, and inches cubed up here. Well, I know 1 inch has 2.54 centimeters, but these units have been cubed. So I need to cube this and cube that. And that makes those cancel. Then inches cubed comes down here, feet cubed up here, and 12 inches is in 1 foot, but again our units are cubed, so we have to cube our numbers. And that made inches cubed cancel. Then feet cubed down here, and miles cubed here. I know that in 1 mile there's 5,280 feet, but again, since our units are cubed, you have to also cube your numbers. And that made feet cubed canceled. I'm now left with the only standing unit of miles cubed, and I'm ready to use my calculator. I'm definitely going to put this number into scientific notation. Well, we need 3 sig figs, so our final answer is 7.10 times 10 to the 6th miles cubed. The 3 systems for measuring temperature. Well, in 1724, Daniel Fahrenheit, there he is, was eventually, he was a lot of things, but eventually he was a glass blower and he made thermometers. And he determined his 0 point by using a mixture of ice, water, and ammonium chloride, which is a salt. And that's where he got his 0 point. I'm not sure why he chose those things, but that's why our 0 point is where it is, which is 32 degrees Fahrenheit if you were just to use water for the freezing point. But he put his 0 point in a mixture, not a substance, a mixture. So if you take ice and water without the ammonium chloride, that's where he set his scale for 32 degrees. And he made a 3rd point of 96 degrees, which was approximately the human body at the time. It's what they labeled it as. We call it 98.6, but he called that blood heat. And from that time, from 1744 until 1954, 0 degrees Celsius by Anders Celsius, we used as the freezing point of water, and 100 degrees Celsius as the boiling point of water. Then along came William Thomson, and in 1954, he determined the correct value of absolute zero as negative 273.15 degrees Celsius or negative 259.67 degrees Fahrenheit. And that is what we know as 0 Kelvin. That is the coldest, theoretically, the coldest possible temperature ever. And the nice part about the Kelvin system is we don't actually use negative numbers in it at all, since the coldest possible temperature is 0. One thing I do like about this is it shows that at negative 40 degrees Fahrenheit, and negative 40 degrees Celsius is the exact same value. That's where these two, the Fahrenheit and the Celsius temperature scales, actually meet. Of these three temperature scales, there's only one I want you to know, and you should already know, and that's that one. These other two, this one and this one, I would provide for you in some formula of one sort or another. Density is a ratio of mass to volume, and we can also use density as a conversion unit between mass and volume. You should know by now already, or I'll just help you remember, the density of pure water is 1 gram per milliliter. That's of pure water at room temperature. At room temperature, yeah. 1 gram per milliliter. So this object would be less than 1. This object would be exactly equal to 1, and this one is less than 1. So if it's less than 1, such as this yellow object, it floats. If it's greater than, oops, I wrote that wrong. Here we go, less than 1. And over here, where it's greater than 1, the object sinks. Yeah. Another way we write the formula is mass over volume. And those are the two sets of units we typically use for density, grams per centimeters cubed or grams per milliliter. Mixtures have variable composition, and they're not a substance. They have different stuff in them, like this picture shows, different stuff. Two different elements are pictured here, but they're all mixed together. So we have two types of mixtures. The first one is homogeneous or homogeneous mixtures, and those look like they're the same. I mean, it looks like a substance. You can't actually see the different parts. A heterogeneous mixture has different parts that you can clearly see. Pizza is a great example of a heterogeneous mixture, whereas Kool-Aid is an excellent example of a homogeneous mixture. A lot of students really enjoyed this Venn diagram, so that's why I put it in your notes, and it allows you to see clearly the difference between mixtures and compounds. A physical change does not change the little arrangements of the balls in a substance. For example, you boil water, you freeze water, it's still water. So before and after, all you've done is change the state of matter of the substance. You have not changed the substance. Now, if we have a mixture, we can use the different properties of physical changes to separate a mixture into its compounds, but it will not allow us, a physical change does not allow us to break compounds into elements. Distillation, we did this lab last year, where you can separate two different liquids based on its boiling points. Filtration, easy peasy one, works really well when you have a mixture of a solid inside of a liquid. Then your filter paper will catch one and not the other. Chromatography is a lot of fun to do. It allows us to separate different mixtures based on their solubility. And there's some pictures of some actual chromatography. It's kind of cool to do. I've seen people use chromatography for t-shirts. A chemical change is what we're going to deal with, obviously, since this is chemistry. And it's when we take different compounds and we break them up, rearranging the little balls, rearranging them into making something completely different with different properties. So, different classes of matter, they're either going to be pure substances, which are the same all the way through it, even on the atomic level, it's the same all the way through it. You have elements, which is just one type of atom, or compounds, which are made up of two or more atoms that are bonded together. Mixtures, there's two types of mixtures. Mixtures contain more than one substance combined. But by combined, I don't mean chemically combined, I just mean mixed up together. So a homogeneous mixture is evenly mixed. You can't visually see that there's more than one thing in there. And a heterogeneous mixture are not evenly mixed. Up next, we're going to start on Chapter 2, Atoms, Molecules, and Ions.